Okay, so this is the time to start our lecture 16 about continuity equation. So we have covered the nonlinear Poisson equation up to now. So if you can successfully follow our lecture contents, then now you can, for example, calculate the equilibrium potential profile at PN junction. So here we have, for example, potential, position, then you can calculate those kind of things. So that is the situation up to now. But you know, this quantity obtained from our nonlinear Poisson equation is just restricted to a certain case where our cathode voltage and anode voltage are the same. So since we have applied the same bias to our cathode and anode, actually there is no difference in the applied voltage. So what is the voltage difference between this point and that point? The answer is simply just 0 volt. Since there is no difference in the applied voltage, so we expect there is no current in this device. So no current at all. This kind of situation is called as equilibrium, and everybody understand the nonlinear Poisson equation is restricted to the equilibrium condition. So today we wanted to talk about how can we generalize our approach to non-equilibrium cases. So that is the main topic our today's lecture. Okay, so let's go to the continuity equation. This slide just to summarize my previous talk. So we need electron density, typically written as N, and hole density, typically written as P, due to their negative and positive charge density. So in this case, electron and hole, how can we calculate it? Because we need this one, the net charge density at a given position. So due to doping, in order to calculate the net charge density, we must know the hole density and electron density. In the case of nonlinear Poisson equation, we have introduced certain expressions for electron density and hole density. Electron density is simply locally dependent on the electrostatic potential. Also, the hole density at a certain point is also locally dependent on the electrostatic potential at that point. So that's the reason why this Poisson equation is called as nonlinear Poisson equation. Where can you find the nonlinearity? So nonlinearity comes from these two expressions. The electron density becomes a nonlinear function of electrostatic potential. The overall Poisson equation becomes nonlinear. That's the reason why we call it as nonlinear Poisson equation. However, please note that the above expressions for electron density and hole density are valid only at equilibrium. Only at equilibrium. So if we wanted to calculate the response of our system called device at non-equilibrium cases, we need a general method. So what is it? So for example, let's come back to our PN junction example once again. So up to now, we can solve the system where the P and are biased to 0 volt. However, you may understand this is not the typical case for our research interest. Usually, we wanted to introduce a certain voltage to our anode. Then we wanted to change the value of this anode voltage. So when we have a positive one, then typically we call it as for bias condition. And if we have anode voltage which is smaller than 0, negative value, then this one is called as reverse bias condition. So depending on the polarity of our applied voltage, so their response, there means that these PN junctions um, uh, really depends on the polarity. And we just measure the current flowing into the device through anode terminal. So that is typical our use case for this kind of a PN junction. So right now we can just consider the case where V anode equal to exactly 0. Then how can we expand our capability to this case or that case? How can we apply non-zero bias voltage to our system? That is our main motivation. But before starting today's talk, I wanted to make some caution about this topic. So maybe some students remember this system, the double gate system, oxide, silicon, and oxide, and we have applied already certain non-zero gate bias to this system. So maybe you remember we have a homework problem which calculate the inversion charge density as a function of your applied gate bias. So you must draw this graph as a problem number 1 of your homework, the last homework. So then you may think that since we have already applied non-zero voltage, for example 1.0 volt, so how can we justify our application of 1.0 volt to the gate? Is this equilibrium or is this non-equilibrium? That is my question. The answer is, even though when we apply 1 volt to these two sides, but here we have a seemingly perfect insulator, oxide and oxide. So therefore, inside this silicon, we cannot expect any kind of current conduction. Okay, that is even true when we introduce a certain voltage difference. For example, let's say that this is just 0.5 volt and 1 volt, but can you expect any kind of current conduction through this system? So this is perfect insulator and this is a perfect insulator. Although we have voltage difference, but it is expected nothing happened in terms of current conduction. So simply speaking, in this MOS system, because this vertical structure is really isolated due to these insulators, so it is okay to apply nonlinear Poisson equation because that is strictly valid for equilibrium case. However, now let's come back to our PN junction. In this PN junction, when we apply non-zero bias voltage here, then what happens? It really conducts current. So in this case, really we are driving our system into the non-equilibrium case. That's the reason why, although we considered already non-zero bias voltage, gate bias voltage in the MOS system. It was allowed to use just nonlinear Poisson equation, and in this new case called PN junction, we are not allowed to use the nonlinear Poisson equation. Okay, so are you all with me? So now I hope that we have sufficient motivation to introduce another way to consider non-equilibrium cases. So simple answer is given here. If we really need to calculate N and P, we must solve additional equation for them. If you wanted to know electron density, then you have to solve an equation for electron density. If you wanted to know the hole density, then you have to solve the equation for holes. So you can now expect your set of equations will be look like this. One equation called as Poisson equation, and another equation for I don't know what it is right now, but an equation for electron density, and finally another equation for hole density. We need these three equations, and these three equations will be the basis for our analysis. Okay, so please understand the need or the reason why we need two additional equations. Okay, do you have any question? Please feel free give me any question on the lecture material. Okay, then now let's go to our next slide. So now our next slide just to answer our previous question. What is the appropriate equation for electron? Or what is the appropriate equation for holes? The answer is continuity equation. So now let's just show you, directly show you the equation of our interest. So this one is the form of our continuity equation. Here I introduce some strange notation like C, but C can be either N or P. So electrons and holes, they can be combined into the same form. Simply speaking, let me just write down once again. The time derivative of our carrier density can be obtained by just flux. If we have net outflux, then our carrier density will be reduced. And if we have net incoming flux, which introduce minus value, then we will have the increase of carrier density. Maybe you remember that we have discussed this kind of concept already in our process simulation part. That is once again given here. Now we consider certain area, and if there is net incoming flux, then C will be increased. And on the other hand, if we have net outgoing flux, then it is obvious that we will have reduction of our carrier density. Then this incoming or outgoing, these quantities is represented by this divergence of flux. This one, just to describe this one. If this quantity is positive, then we can say that the flux is outgoing, and if this is negative, then flux is incoming. So that's the reason why we have here negative side to balance the physical meaning. Okay, so now For electrons and holes, we can have a unified form of our continuity equation. And we have seen it before in the process simulation. So now let's go to the next part. Of course, as I told you before, this continuity equation itself is quite general, not only in this device simulation, not only in the process simulation. If there is certain phenomena related with counting numbers or counting the density, then continuity equation is always involved. However, the more important topic we must consider right now is, okay, then how can we express this flux? Which expression is required to describe our flux? That is our main question. So in order to answer that question, our answer is like this. The flux of a certain carrier, for example, electron or hole, is related with the current density J. So here C, once again, can be either P or N. So we can define some quantities like J sub N or J sub P. So please try to understand the physical meaning of this J sub N and J sub P. This is electron current density, and this is similar quantity but hole current density, and they have the unit like ampere per square centimeter, and also this one is ampere per square centimeter per unit area. How much current is flowing? That is the quantity called as this one. Then we have the relation between these two quantities. So upper sign for holes and lower sign for electrons. So let me just write down hole current density is just positive Q times Fc, and J sub N, electron current density is just minus Q times F sub C. Oh, sorry about that. C must P here. So C must N here. So simply speaking, since our holes are carrying positive Q charge, so we must multiply positive Q to calculate the current density. On the other hand, in the case of electron carries minus Q, so that's the reason why we must multiply this quantity. Okay, please note that flux is just counting the numbers of particles crossing the unit area and unit time. So when we apply minus Q or positive Q, whose physical dimension is just Coulomb, then we will have, following this relation, we'll have Coulomb per square centimeter and second. As you know, Coulomb per second unit is typically called as the ampere. So that's the reason why we have balanced relation between two different quantities. Please check the dimensionality. Okay, so right now what we have learned up to now is we need to understand the flux, and flux is really directly related to the current density, but still we don't have any information about what the current density looks like. what is form of J sub n? What is form of J sub p? Okay, although we can say this way, but this is not the solution. We need to express these two quantities, for example, in terms of hole density and electrostatic potential. Also, in this case, we need to express this electron current density in terms of electron density and electrostatic potential. These jobs are more important to just stating that J sub P can be related to the flux or J sub N can be related to the flux. So what is it? What is the suitable form for our current densities? That is the most important question right now. Okay, do you have any question? So please, whenever you have any question, then please interrupt me. Then now let's go to the next slide. So the answer is shown here. Once again, I think that you feel the similarity. So similarity with our current approach and our process simulation, diffusion simulation. But that's true. Here, for electrons, we just introduce a sum of drift term and diffusion term. And in the case of holes, also we introduce drift term and diffusion term. So simply speaking, we are now expressing the current density as a sum of drift, drift and diffusion. So if you ask me a question about is this the only way to express this current density, then I would say that it's not. We may have alternative form. However, this is the most widely used one, and drift and diffusion. So that is in many cases just simplified, short-handed, like drift diffusion (DD), but yeah, that is quite much popular in this terminology. Okay, so for electrons, we have drift once again, drift and diffusion, and here we have drift and diffusion, and maybe you feel the similarity. Even in the case of our diffusion case, we consider the flux, and of course flux is more or less related with something like this, dc over c. However, at the end of our previous diffusion simulation part, we introduce another things related with electric field. So now you understand actually our previous treatment for diffusion flux in the case of diffusion simulation is identical to this fluxes. So now please understand this one. Although we are considering three different species, one is dopant. This is atomic core, and electron, it is much smaller one, small particle, and hole, it has a different polarity. So we have three different species, but the description about their movement, what is your feeling about that? They are all treated in a unified manner. So diffusion and drift, yes, because they are charged particle and there occurs significant gradient in their concentration. So these two physical mechanisms become most important one we have to consider. Okay, but then if we have similarity, then your natural question is, wow, then we have already covered this kind of problem in the diffusion simulation, so maybe we can apply the same capability or same approach to this electron transport and hole transport. But I have to admit that our previous approach for this electric field treatment was quite crude. So do you remember this one? How did we consider this electric field? So electric field was just represented as this kind of gradient of electrostatic potential. It is not an approximation. However, after that, this electrostatic potential was just expressed as a function of electron density under the assumption like this: electron density, and yes, in the case of our n-type dopant, we applied this kind of approximation. So please note that this kind of approximation can be valid only at where equilibrium cases. So simply speaking, when we consider the diffusion simulation, we have applied an approximation which is valid only at equilibrium case to non-equilibrium cases. So there really exists inconsistency. We have made something weird. However, we just did it. Now, instead of that, we will not introduce this kind of approximation. So previously we made additional approximations, but however today we will go without that kind of approximations. Okay. Then before talking about the implementation of this kind of expression, I wanted to simply or shortly talk about derivation about the continuity equation and form for current density. The first question is, how can you derive the continuity equation? So although we feel the continuity equation seemingly quite much acceptable, however, this is just a feeling. Is there any way to derive the continuity equation from more physics-based equation? So yes, we have. It can be rigorously derived from the Boltzmann transport equation. So from the Boltzmann transport equation, you can rigorously derive continuity equation in the form like this one. This form can be well obtained from the Boltzmann transport equation. What is the Boltzmann transport equation? In the Boltzmann transport equation, we introduce a quantity called distribution. Oh, sorry about that. This is my typo. This is not R. This is time variable t. Sorry about that. In this distribution function, we just describe a certain quantity at a time instance t and position r and wave vector k. Let's say that there is one electronic state. There is one state. Then this distribution function is just to describe the occupancy of a state. Okay, so are you with me? Of course, we are now talking about just coarsely grained system. So R and K should be regarded as a certain gridded point. So although we have many different states there, but anyway we can try to find out the average occupancy of these states, and the average occupancy of these states is represented as this distribution function. So if we really wanted to know how many electrons are there, then we must consider two quantities. So if there is one state, how it is probable to be occupied, and another quantity is how many states are there. So now think about this one. Let's say that there is a hole and there are many seats here, and we wanted to do certain recital by a very famous musician, and we wanted to sell those seats to our audience. Then if we have, for example, 12 seats, and if we have just 50% of selling percentage, then we can expect that, okay, then we have 6 persons in this room. So this is like this product. Here we have number of seats or number of states that is described by this density of state, and if one position, if we have one seat, then how probable it is filled, then that is described by this distribution function. So now density of state is more or less assumed to be a given number. If we have a certain energy value, then from the bulk density of state, we expect that the density of state is given. So, simply speaking, this one is a function of your kinetic energy. And here we need certain position and k, t, and this wave number is more or less related with our kinetic energy. We can find a one-to-one relationship between our momentum k and kinetic energy. So therefore, when we consider these two quantities, this is relatively easier to consider, and this quantity is more difficult. But once we know the distribution function, then from this product we can calculate the electron density or hole density rigorously. Okay, do you understand this motivation? So Boltzmann transport equation is far more fundamental than the just continuity equation. So actually this is the master or governing equation in the semi-classical transport theory. So the thing we can derive continuity equation directly from the Boltzmann equation strongly support that we can believe this continuity equation. Good, perfect. But if we go to the next topic, how can we derive the current density? Can we also derive this current density out of the Boltzmann transport equation? The answer is partially yes. I mean that also from the Boltzmann transport equation, the governing equation of semi-classical transport, we can try to derive the current density. Actually, the form you are currently looking at, these forms are derived from the Boltzmann transport equation. However, unfortunately, the derivation procedure is not straightforward as like the continuity equation, and actually we need more terms here. However, we neglected those terms, and also here we have these terms, and we need certain expressions. So, simply speaking, I wanted to say that continuity equation itself, there is no arguing point in its derivation. So we must believe this continuity equation. And in the case of current density, this is not the only way to express the current density. Drift diffusion is not the only way. We can find more advanced approaches. So they are typically called as hydrodynamic model, or even higher models are available. However, in practice right now, these kind of higher order models are disappearing because simply speaking, these kind of more advanced equations are too complicated or too computationally inefficient, and the improvement of accuracy is not that much significant. Okay, so are you with me? So there is always a trade-off between this one. So your accuracy and physical and computational efficiency. So if you spend more effort, then you will get more accurate result. And if you spend less time, less computational resource, then your answer will be less accurate. That is quite much understandable. However, the point is, if you spend more effort for this kind of advanced models, however, improvement of the accuracy is sometimes is not that much, or sometimes it is going worse. That's the reason why right now people don't actively using this kind of advanced transport model. Then instead of that, they just calibrate the parameters inside this drift diffusion model. So what is the parameters? So more or less parameters are this mobility and diffusion constant, and mobility and diffusion constant. These two quantities are main knobs in our calibration. And even importantly, we just introduce Einstein relation in many cases. Do you remember this relation? So Einstein relation simply means that diffusion constant and mobility are related with this constant, so thermal temperature, constant proportional coefficient. So these can be just merged into only one quantity, mobility. So simply speaking, so right now people are more or less just calibrating their electron mobility and hole mobility to calibrate the, the model parameters to fit their experimental data. Okay, that is the situation. Then of course you may have some question. Is this really justifiable procedure? So should we follow more rigorous one? But you know that we are working in the engineering side of semiconductor technology development. So if it is too much computational expensive, then it's not possible to pursue that way. So right now this is the compromise between the accuracy and efficiency. Okay. Do you have any question? Okay. Okay, then let's go to the next topic.
수동자원 나왔습니다. 수업 중입니다. 수업 중. 예, 그럼 좀 넘어가겠습니다.
Okay, then so I wanted to say that if we have sufficient time, then actually in our regular course we must follow the derivation procedure. However, unfortunately, I think that it is more suitable to just introduce this final form and just go to its implementation. If you are interested with the derivation of this continuity equation and current density, then please come to me, then I can suggest you more references for your own interest. Okay, then now let's say that, well, anyway, we wanted to just implement this continuity equation. We must implement electron continuity equation and also hole continuity equation. So we must do these jobs twice. However, I will just show you one continuity equation, electron continuity equation. You can just repeat this one once again for your whole implementation. So if we have steady state means that any kind of time derivative terms goes away. Then this is our original continuity equation, but this time derivative terms goes away because of our steady state approximation. So now it can be simply written as, okay, divergence of our current density should vanish. That is the simple form of our steady state continuity equation. So this is closely related to the equation called Kirchhoff's current law. So if we have a certain node, circuit node at in a circuit, and let's say that there are 3 branches. Okay, so are you with me? I mean that there can be a certain resistor and resistor and resistor, and say that this is the meeting point of 3 different branches. Then what is the KCL? Kirchhoff's current law just stated that the sum of all our outgoing branch current should be 0. So this is nothing but just a realization of this vanishing divergence of our current density. Okay. Anyway, now simply speaking, we are now talking about current conservation. Steady state. Then now let's try to consider this electron current density. Electron current density has 2 terms, like drift term and diffusion term. However, using the Einstein relation, we can just express our mu n mobility as dN over Vt, thermal voltage. This is simple relation. So now we can eliminate the mobility and also introduce only this diffusion constant. We did it already in the case of diffusion simulation, process simulation. And previously, the point where our previous approach became wrong was just to introduce certain approximations. Okay, electrostatic potential can be expressed as, for example, Vt times log n and intrinsic carrier density. Yes, this is strictly valid only at equilibrium, but we applied it to non-equilibrium cases, so that was problematic. So we do not use this kind of approximation any longer. We just keep it there. So now we must solve both the electron density and electrostatic potential. Then I wanted to ask this question. Basically, this electron continuity equation is the equation for electrons. Okay, so electrons are covered by the electron continuity equation. But here we have electrostatic potential. Then which equation care about the potential? Do you remember? Electron, these quantities are calculated by the electron continuity. Then what is the equation for electrostatic potential phi? Do you understand what I'm saying? So in the case of potential, our Poisson equation gives the information about this electrostatic potential. So therefore, we must solve our electron continuity equation together with the Poisson equation. Only when we solve these two equations together, all together, then we can get the self-consistent solution. Okay. So now let's go to our specialized case, like a one-dimensional case. So if we adopt a one-dimensional case, then now we can assume that the vector quantity of J sub n can be represented as this scalar quantity. So for certain direction, let's just call it as x direction. So then we can write down in this way. If we adopt this one-dimensional approximation, then this kind of current conservation rule can be just becomes this one-dimensional derivative with respect to x of our J sub n. So are you with me? So simply speaking, this is a three-dimensional form, and this is x, y, and z, that is this gradient operator, that operator, and here we have only Jn times x, and of course this Jn is only function of x, not dependent on y and g. So when we have this kind of situation, then partial derivative with respect to y goes away. This one goes away. And here we have unit vector aligned to x direction and unit vector aligned to x direction. They are just merged into the unit quantity, and the remaining thing is just round J sub n over round x. That's the reason why we have finally this form, the reduced form in the case of a one-dimensional structure. Okay, so it's not that difficult, and now let's consider the current density. Then if we just reduce the dimension, then QD is okay, and this gradient becomes just first order derivative, and here we have also first order derivative. This is not that difficult to understand. Well, although it's not that difficult to understand, implementation is a little different story. So now we must implement it into our system. How can we do that? So we have already seen many times about the box method. Box method simply means that we integrate our flux term over certain area, then it becomes just a surface integral area or surface, okay, surface, and now we integrate it over its surface area. This box integration can be done, but if we consider one-dimensional, it is really simple. Starting from one point, one end point, and the another end point, lower and upper limit, we can just integrate this system. So this system, continuity equation, is even more simpler because previously when we considered the do you remember the Poisson equation in one-dimensional case? So it looks like this: low and derivative of what? Derivative of our displacement, but that was written as minus. Yes, that was the form of our previous Poisson equation. But right now we are considering even more simpler form, like we have no source term. Yes, this is 0. And previously we had more complicated form, but this is just merged into j sub n. Of course, j sub n has this long expression, but for a while, just forget about it. Then, now our integration becomes really simple because it is already done in the first order derivative. Then simple integration gives us just the difference between j sub n evaluated at upper point. This is upper point and this is lower point. So what we have to do is just to evaluate our current density at upper point and lower point and get the difference between these two quantities. Okay, let me just repeat once again. In the case of one-dimensional case, we can have xi. Then what we have to do is evaluate your j sub n at this upper point and this lower point and make the equation between them. Okay, I mean that the flux or the current density calculated at this point is equal to this point. At x sub I, we can introduce this kind of thing. Okay, then let me just give you a simple question. Now let's say that we have only 4 points in our entire system. Okay, let's say that we have only 4 node system. Then we wanted to apply this kind of discretization. Then please consider the equation for this second node or first node. For example, let's say the x0, x1, x2, x3. Then by applying this continuity equation, what we can get is quite simple. Okay, Jn evaluated at 0.5 is equal to what? J sub n evaluated at x sub 1.5. This is governed by this x1 equation. Are you with me? Then please consider x2 point. What x2 point state is the quantity evaluated at x sub 1.5 is equal to what? Equal to j sub 2.5. So as an application of these two one, then we can say that okay, j evaluated at 0.5 equal to 1.5 and equal to 2.5. The next question is, okay, we understand j is constant over the system, but what is j itself? So even when they are all 0, this equation holds, and they all becomes 1, it's okay. 10, 100. So actually, by applying only this kind of things, then we cannot get the actual value. Okay, it just states that okay, we have certain continuity. Current is conserved. Then conserved to what? Which value? That is related with this expression. So this expression is now covered. So how can you calculate or discretize this equation? J n contains both derivatives. One derivative with respect of electron density with respect to the x, and another derivative of potential once again with respect to this position. So how can we make a discretization? This is quite much important question. Actually, I want to emphasize that this is as much as TCAD device simulation is involved. This is the most important instance you are studying in this semester. We have, please note that once again, I want to emphasize this point once again. Here we have two different derivatives. And right now we have to start how can we consider the discretization of these two terms. That is the most critical issue in this lecture, in this semester. Why? So we will see it later. But right now, if we just evaluate this quantity at I plus half, then we must calculate these quantities. So first derivative of electron density at the midpoint, and also this n times d phi over dx evaluated at this midpoint. Seemingly good. Then if I ask you that question, what is your answer? Wow, dn over dx evaluated at a midpoint. Then maybe you can say this way: xi plus 1 and xi. dn is shown here, and we must consider also dx. Yes, this is dxi plus 1 minus xi. Are you with me? So I just applied the linear approximation to our electron density and just to calculate or suggest one simple expression. Then let me just follow once again the same way. Here we have d phi over dx. Then how can you calculate this d phi over dx at a midpoint? Then phi evaluated at the upper point and lower point and takes the distance between them. So I just considered this first order derivative. And here we have n evaluated at what? evaluated at the midpoint. Unfortunately, we don't have this expression or this quantity. And electron density, we know electron density evaluated at upper point 2. We know it because a node is assigned, and we know xi. We know it because this is included in our solution variable. But if I am asked to answer that question, it is very confusing because half point electron density, what is it? Please give me that information. That's the main cause of problem. Although we made a linear approximation, so right now we have direct information about this one. If we just strictly follow the linear approximation, what you can do is quite simple. Since this is just a midpoint, then I will just take the average between them, arithmetic average, then we will get the electron density at the midpoint. So you know that in the simplest approach, what we can do is quite simple. Apply the linear approximation between two neighboring nodes everywhere. When we calculate the derivative of electron density, we just applied linear approximation. When we interpret the midpoint electron density, we just took the arithmetic means to follow the linear approximation. So also in the case of this d phi over dx, we just follow the linear approximation. It is quite simple-minded and seems to be quite straightforward. So now let's go to this is the result we can follow. D phi over dx is just given as just linear, following the linear approximation, and here we have, yes, this is the d phi dn over dx, and this is the d phi over dx. Of course, here we have delta x here, so combined with this one, we have dn dx, and this is d phi over dx. And you can find that here you have something, here something is related with and evaluated at a midpoint. Similar thing can be found for Jn at x sub I minus half. So can you do it correctly? So please try to write down. So you have most of you have actually all of you have a tablet. So please try to do your equation. So please write down, not just looking at my slide. For example, if we have here minus sign, then maybe we have this one, and here we have a minus 1, and of course we must have an I minus ni minus 1, also an I and ni minus 1, and yes, we can just shift our I value, I index, I subscript to I minus 1, and our subscript I plus 1 to I. Then it is sufficient to get the expression for j sub n evaluated at another midpoint. Okay, so are you all with me? This is not that difficult, and more careful treatment is required when you consider whole current density. whole continuity equation is actually has the same form, so that's not that difficult. But when you evaluate the whole current density, you should be a little bit careful, because what is the difference between this electron form and hole form. So now you can understand we have sign difference. So here we have overall minus sign, and also once again positive sign, because when we consider these two terms minus positive, so we have overall minus sign for our diffusion term. Oh, sorry about that. This drift term. Also we have positive and minus, so we have also overall minus sign for drift terms. Please note that when we come back to our J sub n and J sub p, we realize that they share the overall negative sign. Both of drift terms for electrons and hole, both of them have negative sign. But in the case of our diffusion term, holes have a negative sign and electron has positive sign. Then when we come back, then now we can understand. In the case of electron, we have overall positive term for our diffusion term, and in the case of a whole current density, we have overall negative sign. So please be careful. To some of you, it is just a matter of sign, so simple mistakes is just acceptable. But it's not actually that really. This sign really determines whether your carrier is positively charged or negatively charged. So please don't make any mistakes in assigning the sign for these quantities. So simply speaking, if you just swap the expressions this and that, then what will happen? Your electron will behave just like holes, and your holes will behave just like electrons. So it is easy to make mistakes. So please don't be confused, and please keep the sign. Okay? So now if we adopt this kind of J sub n and J sub p, then we can calculate also Jacobian matrix. So actually, so please understand this one. Although I have shown some quantities like round Jn over round n, round Jn over round n, but it is now assuming that you can now do something like this. Now let's say that we wanted to calculate a certain residue. Instead of this capital letter, I just wanted to use small letter Rn. This is a residue vector on entries for your position x sub I. Your residue is simply given by what? Simply given by Jn evaluated at positive half minus Jn x I minus negative half. This is your Rn. So in order to calculate the Jacobian matrix, what you have to do is now take partial derivative of your residue function with respect to what? With respect to our solution variables. Your solution variables should be like this: n I plus 1, also n I, also n I minus 1, also phi plus 1 phi I phi I minus 1. You have to make the partial derivative of your residue function with respect to all three electron densities and all three electrostatic potentials. Okay, are you with me? Because you know we are now talking about certain position called xi, and it has two quantities, electron density and electrostatic potential. And we are talking about the neighboring 2 points called as x sub I minus 1 and x sub I plus 1. They all have also another pair like n phi and n phi. So when you evaluate this residue function, then your residue function will dependent on these 6 quantities. So you must calculate these dependencies. Okay? So now what you have to do is like this. First of all, let's just think about the first case. Oh, I wanted to calculate something like this. Something like round Rn over round n, which is evaluated at xi plus 1. Okay, so are you with me? In this case, what we can do is, since R is so simple, we can individually Jn evaluated at 0.5 and I plus 1 minus Jn evaluated at minus 0.5 and xi plus 1. But fortunately, this guy have no dependence on this positive or upper point density. We are now talking about this quantity, and we are now talking about the current at this position. Are they related or not? They are not related. This flux or this current density only dependent on these 4 quantities, not this n density. So this second term goes away immediately. So now we must calculate only this quantity, the first term. Then now it's time to consider this one. Yes, here we have some terms like this. Partial derivative of our j sub n with respect to our n I plus 1. Then if we follow this previous form, this previous simple form shown here, the form shown here, then we can take the partial derivative. Please try to make a partial derivative. Then what will happen? Yes, this one will contribute q times dn over xi plus 1 minus xi, because when we take partial derivative, this just contribute to unity, and this one goes away because this is ni, not ni plus 1. And how about the second term? The second term here, if we take the partial derivative once again, then that will give us 1 over vt and half. Are you with me? So when we take the partial derivative of this term, it will give us just half. And now we have phi I plus 1 minus phi I. That is the partial derivative of our current density with respect to n sub I plus 1. That is shown here once again. Let me just repeat it. Yes, here we have 2 times Vt, So this is just 2 times VT, and you can find it. So I hope that I did not make any mistakes in my notation and equation. So please check whether I made mistakes or not. So you can do it. Quite simple. So these two cases are quite simple. And now let's go to the case of potential differentiation. Then this diffusion term doesn't have any kind of potential difference. So simply this term immediately goes away. Then if we wanted to calculate the partial derivative with respect to phi I plus 1, then it will contribute minus 1 over Vt I n plus 1 and I. That's it, because this one contributes to 1. So now you know that we have this form and another form. Okay, so we cannot follow this full implementation in the today's lecture, so we will continue the discussion. But today we have no homework, because I think that you must spend your time on our previous homework. So please concentrate on your previous homework, and please also review our today's lecture contents, and we will continue the discussion on the continuation next Monday. Okay, on the today's lecture. Thank you.